All right, so now we're going to talk about how to deal with the issue of small pivots through what is known as pivoting. And the basic idea behind pivoting is to either reorder the equations or to reorder the unknowns so as to avoid having these small, close to zero terms. It's like along the diagonal, it's like where you divide by them, okay? So let's look at three cases. All right, so the standard one is no pivoting. Okay, where if you have some sort of matrix, and then you have, say, a term here, right? You transform it. You use that, whatever's on that diagonal at that point, to zero out the entries below. Okay, so that's one possibility. The second possibility is you choose a pivot in the same column. Okay, which might look like the following. Okay, so you might use this entry instead of the one here, which is what you would normally do, and then you would transform it in the following way. Okay, so again, you would add some multiple of this equation to these other two equations so as to zero out those entries, right? So that's pivoting in the same column. So you look at, you look at this entire thing, and then you try to see which is the pivot which is the best in some sense. And then the third possibility is you choose a pivot somewhere in the submatrix. I should say that when you say the same column, we don't mean the things which are above that, because you already those have already been transformed, so you don't really want to touch that. So let me again try to draw a picture for you. Right. So essentially what happens is, for example, you might choose a pivot somewhere in this block, this sub-block, right? And if you do that, again, the goal is to choose an appropriate multiple of that row so as to zero out the corresponding entries in the same column, right? Okay. All right. So so this is what is called complete pivoting. So you have to find an entry, right? You want to find largest entry in a submatrix, which is n by k by n by k. So this is very expensive to do complete pivoting. So it's of the order of n times n minus k times n minus k, right, which something looks like n cubed. So it's as expensive, or up to SLU, so that's something you might want to avoid. Okay, so instead it's like what is common So no pivoting is oftentimes a problem because, again, if that diagonal entry is small, then it messes everything up. So no pivoting is usually not an option. It results in a LU algorithm which is potentially very unstable. And of course, complete pivoting can be very expensive. So instead, what people do most of the time is do what's called partial pivoting, which is sort of this intermediate case, where you look for a pivot in the same column. This is called partial pivoting. Right, and it takes about n times n minus k, which is of the order of n squared flops, so it's much less expensive. And for most applications, it's good enough, right? So that's what people do in general, is what is called partial pivoting, where we sort of essentially reorder the equations. Okay, so if you recall, it's like, one of the things we've looked at before is using matrix products to basically realize the effect of elementary row operations, right? So this is how we realized Gaussian elimination as matrices acting on the coefficient matrix. So now we need to do something which is analogous to swapping the order of the equations. So the natural question to ask is there then a matrix which represents the swapping of rows in the coefficient matrix? And this leads to the idea of what are called permutation matrices. So that's what we'll be talking about next. Okay, so these are called permutation matrices. Okay, so a permutation matrix is the identity matrix with two or more of the rows or columns interchanged. Okay, so as an example, if I start with the identity matrix, say 1, 1, 1, this 3 by 3 identity matrix, and say I swap the first and second rows, right? And what I get is the following: 0, 1, 0, 1, 0, 0, 0, 0, 1. And so let me sort of just state the following observation or fact, that if you pre-multiply A by this permutation matrix, then you will exchange rows in A. All right, so hopefully by now it's like you realize that if you multiply on the left, you end up getting row operations, and if you multiply on the right, you get column operations. So if you pre-multiply the matrix A by P, so you're multiplying A by P on the left, then you will exchange rows, and as you might expect, if you multiply A by P but on the right, you will exchange columns. Okay, so that's something you can check for yourself, but let's just look at a specific example of this P matrix acting on a coefficient matrix. So let's look at an example. So let's say with P is this 0, 1, 0, 1, 0, 0, 0, 0, 1, and A is A11, A12, A13, A21, A22, A23, A31, A32, A33. and you write down P times A, right? Then it's easy to convince yourself that what you get is A21, A22, A23, A11, A12, A13, A31, A32, A33. Okay, all right. So if you recall, the way we got this P matrix was we interchanged the rows 1s and 2. Excuse me, it's like on the identity matrix, and when you take that matrix P and you multiply on the left, it's like you multiply A, it's like on the left with P, then it has the net effect of swapping rows 1 and 2 as well. So hopefully you'll see that quite clearly. And if you're not convinced, you can work out the details of this matrix product yourself. Okay, so all right, so that's that's a big part of the picture now. That you have these permutation matrices which have the net effect of interchanging rows of a of a coefficient matrix, and that's of course what you want to do when you do what is called partial pivoting, which is that instead of choosing something which is on the diagonal, you allow yourself to choose anything that's like on that column at the diagonal or below, okay, as your pivot, okay. So let me just stop here for now. It's like, and the next thing we'll do is to talk about what happens when you modify LU to allow for the possibility of partial pivoting, which means that you get to reorder the equations as you go along. So let me just stop here for now.